Hi, I'm Eli Hart.
And I'm Yvonne Wong.
We're staff engineers on Airbnb's Android platform team, where we work on frameworks, build tools, and CI systems to support over 100 Android contributors at Airbnb. Today, we're going to talk about Trio, an Android architecture we've created that's built on top of Compose UI and our Mavericks open source library.
So Airbnb originally open sourced Mavericks in 2018 to simplify and standardize how state is managed in a Jetpack view model. It's been very successful at Airbnb over the past 5 years. Mavericks is used in virtually all of the hundreds of screens in our app, and we've heard from other companies that it has worked well for them too. So for those of you unfamiliar with Mavericks, I'll explain briefly how it works, since that will be important in understanding Trio. At a high level, Mavericks is fairly straightforward. It enforces the pattern that all data exposed by the view model must be contained within a single data class. In this simple counter example, this will be the current count. State properties can only be updated in the view model via calls to setState. The setState function takes a reducer lambda, which given a previous state, outputs a new state. We can increment our count by simply adding 1 to the previous value. The base Mavericks view model enqueues all calls to setState and runs them serially in a background thread. This guarantees thread safety when changes are made in multiple places at once, and ensures that changes to multiple properties in the state are atomic, so the UI never sees a state that is only partially updated. Mavericks view model exposes state changes via a coroutine flow property. When paired with reactive UI, like Compose, we can collect the latest state value and guarantee that the UI is updated with every state change. Our engineers have enjoyed Mavericks because it is conceptually simple and requires minimal boilerplate, while still being flexible and powerful enough to drive our most complex screens. We find it easy to mock and test, and like that it builds on top of the standard view model in Android Jetpack. So, why did we invest in building Trio? Before Compose, we paired Mavericks with a fragment-based architecture, which had limitations with navigation and testing. As we looked towards adopting Compose, we saw a chance to become Compose first and move away from fragments completely. By switching to pure Compose, we can better prepare for future Android investments and eliminate years of accumulated tech debt in our fragment-based architecture stack. With Trio, it was important to us to continue using Mavericks so that we wouldn't have to retrain engineers or rewrite existing view models. Most importantly, Mavericks fits very well with Compose and unidirectional data flow. With fragments, we struggled to guarantee type-safe communication between screens at runtime. We didn't feel our needs were fully met by the Jetpack navigation component, especially given our heavily modularized codebase and large app. We looked for a new architecture that could provide better type safety and modularization support. We wanted an architecture that would improve testability over fragments, such as more stable screenshot tests and simpler navigation testing. We considered open source libraries, workflow, and ribs, but opted not to use them because they were not Compose first and were not compatible with Mavericks and our other pre-existing internal frameworks. So with these requirements in mind, we decided to build our own solution, Trio. Let's now take a look at how we approach Trio's architecture design.
Thanks, Yvonne. Trio is an opinionated framework for building features. It helps us to define and manage boundaries and state in Compose UI. Self-contained blocks are called trios. Each trio has its own view model, state, and UI, and can communicate with and be nested in other trios. Trio standardizes how state is hoisted from UI and how events are handled. This enforces unidirectional data flow. The view model makes changes to state via Mavericks reducers. The UI receives the latest state value to render, and events are routed back to the view model for further state updates. Trios can be nested in any configuration. Parent trios create children with initial arguments through a router, and then communicate with children through a flow of props. These props provide data, dependencies, and functional callbacks. The framework helps us to guarantee type safety when navigating and communicating between trios, even across module boundaries. This design was inspired by Square's workflow library, but Trio differs in that it was designed specifically for Compose UI and uses Mavericks view models for managing state and events. Each trio can be tested individually by instantiating it with mocked arguments, state, and props, coupled with Compose's state-based rendering and the viewmodel's immutable state patterns, this provides controlled and deterministic testing environments. Now, let's look at concrete details of how the architecture is implemented. Each trio implementation starts by subclassing the trio class. A trio can be used to represent any size UI element, but for this example, let's assume the trio represents an entire screen. Each screen has a router annotation, which hooks it into our navigation system. The trio class is typed to define its args, props, state, viewmodel, and UI. And while the boilerplate of defining these types adds some friction, we found it necessary to provide sufficiently type-safe navigation and inter-screen communication. When a trio is created, it must be passed either an initial set of arguments or an initial state. These are passed to the class constructor through an initializer. Note that going forward, in many of our code examples, we're omitting or fudging the type arguments and constructors to simplify the example, so don't overthink any inconsistencies there. The role of the trio instance is to create and manage its state, viewmodel, and UI. Its functions are overridden to control how each class is instantiated. The initial state is generally created from the arguments that the caller passes in. While args and props are similar in that they both provide input data to the trio, there is one fundamental difference. Arguments do not change over the life of the trio, while props are dynamic and can be updated at any time via a flow. This was an important distinction to us because we want to guarantee that static information, such as the starting count or some ID, will never change. Codifying that assumption makes screens simpler and more robust. When creating a new viewmodel instance, Trio provides an initializer to wrap the initial props and state values that the viewmodel needs to function. The initializer also passes along information such as the Trio's unique ID, its flow of props, and a reference to its host activity. If the viewmodel needs any dependencies from the application's dependency graph, this is where we access the graph to pass those dependencies to the viewmodel. Finally, the UI class wraps the composable code used to render the trio. The UI class receives a flow of the latest state from the viewmodel and also uses the viewmodel reference to call back to it when handling UI events. We like that grouping these factory functions in the trio class makes it explicit how each class is created and standardizes where to look to understand dependencies. However, it can also feel like boilerplate sometimes. So, if desired, a layer of tooling, whether reflection or code-gen based, can be added on top of this to automate it. For example, we use reflection to create the UI class since it never needs any customization, and we use assisted inject to automate creation of the viewmodel with Dagger dependencies. Once we've created the trio instance, we can render it in UI. Each trio has a corresponding UI class typed with its state and viewmodel. It implements a single composable function named content, which determines the UI that the trio shows for a given state. The function has a trio render scope receiver type, which allows us to customize the trio's animations. While a top-level function could have been used here, Trio's design uses an interface to represent the UI because we wanted to be able to codify the state and viewmodel types, properties, and arguments. The content function is implemented to display our desired UI. For example, a trio representing an entire screen might display a top app bar with some text below it. The content function is recomposed every time the state changes, and all UI events, such as clicks, are directed back to the viewmodel for handling. This design enforces unidirectional data flow, which means that testing the UI is easy because it is decoupled from the logic of state changes and event handling. It also standardizes how composed state is hoisted for consistency across screens, while removing the boilerplate of setting up access to the viewmodel state flow. One trio design decision to note here is that we handle events simply by calling functions on the viewmodel. Alternative approaches might define actions as a sealed class or as functions on an interface, but we don't like the added indirection and boilerplate that those options introduce. One benefit of those alternatives might be simpler testing, but in practice, we find it very easy to mock the viewmodel for tests. One other thing to note is that we don't want the UI to access any properties or functions of the viewmodel during composition, as this breaks unidirectional data flow and can cause various compose issues. The viewmodel must only be used to invoke functions for event handling. We enforce this via our test tooling so that engineers can't accidentally misuse Trio. Given a Trio instance, we can render it by invoking its content function. This allows us to place it wherever we like within a compose hierarchy. A compose modifier gets passed along to a box that the Trio UI is placed in so that we can modify its layout if needed. To enable customizing entry and exit animations, the content function also takes a Trio render scope, which wraps an implementation of Compose's animated visibility scope. The content function within the Trio class is fairly simple at a high level. It uses the previously mentioned factory functions to create initial values of the viewModel, state, and UI, reusing them when possible. The state flow is collected from the viewModel and passed to the UI's content function, which is wrapped in the box to respect the constraints and modifier of the caller. In practice, the actual implementation is quite a bit more complex because of tooling and edge cases we need to support, such as tracking the trio's lifecycle and managing save state. You've now seen how the trio class works and how it is used to render a state to UI. Next, we'll look at how trio instances are stored in state. Trios are stored in the viewModel state alongside all other data that a screen exposes to the UI. For example, a common use case is to store a list of trios to represent a stack of screens. The trios get saved across process depth because they are parcelable, and we apply the persist state annotation to the property holding them in the state class. This annotation is a mechanism of Mavericks that automatically saves and restores parcelable and serializable state values. The viewModel controls the state and can expose functions to push a new screen or pop off a screen. Since the viewModel has direct control over the stack, it can also perform more complex navigation changes, such as reordering screens or dropping multiple screens. This makes navigation extremely flexible. The UI accesses the trios from state and chooses how and where to place them. We can implement the screen flow by showing the latest trio in the stack. It's not an obvious design decision to manage navigation by storing trios in state. Alternative approaches might instead use a navigator object directly in the UI. However, Trio's approach allows the viewModel to update its state and navigation in a single place. This can be extremely helpful when we need to delay a navigation change until after an asynchronous action, like a network request, completes. The inability to do this easily with fragments was a major pain point for us. With Trio's approach, our navigation becomes simpler, more explicit, and more easily testable. For example, the viewModel can handle a save and exit call from the UI by launching a coroutine with a suspending network request. Once the request completes, we can pop the screen by updating the trio stack in state. We can also atomically modify other values in the state at the same time, perhaps based on the result of the network request. This easily guarantees that navigation and other state stay in sync. As the navigation stack becomes more complex, navigation hierarchy gets modeled by a chain of viewModels. As their state is rendered, it creates a corresponding compose UI hierarchy. This can take the form of screen backstacks, split screens on a tablet, screens in a view pager, or even small sections within a page. There are two nice benefits of modeling navigation like this. One is that it becomes simple to specify custom state values when testing. We can easily create whatever navigation states we want for our tests. Another benefit is that since the navigation hierarchy is decoupled from the compose UI, we can preload trios that we anticipate needing simply by initializing their viewModels ahead of time. This has been a performance game changer for us since preloading pages is now so easy. Normally, a complex object like a trio is not allowed in the Mavericks state, and doing so actually adds a lot of complication because we need to be really careful about how we manage its lifecycle. However, we found the benefits to be worth the extra complexity. Ideally, applications with the trio could use a single activity. However, especially for interop purposes, trios will sometimes need to start activity intents. Traditionally, this isn't done from a viewModel because viewModels should not contain activity references. However, in order to keep all navigation within the viewModel, trio makes an exception. As alluded to earlier, the trio viewModel is given a flow of activities via its initializer. This flow provides the current activity that the viewModel is attached to, or null when the activity is detached, such as during activity recreation. When needed, a viewModel can access the next non-null activity instance via the await activity suspend function. Here we can use it to start the next page in a new activity after a network request completes. While a bit unorthodox, this pattern has worked really well for us, and we've enjoyed being able to co-locate all navigation calls with other business logic in the viewModel. Let's turn to how trios are created. Trio's navigation system is designed to fit with the modularization structure of Airbnb's codebase. To allow faster build speeds and explicit ownership boundaries, we've split our codebase into over 1,800 modules. Each module has a specific type, indicated by its prefix and suffix, which defines its purpose and rules for which other modules it can depend on. Feature modules, prefixed with feet, contain our trio screens. Each screen in the app might live in its own separate module. To prevent circular dependencies and improve build speeds, we do not allow feature modules to depend on each other. This means that one feature cannot directly instantiate another. Instead, Each feature module has a corresponding navigation module, suffixed with nav, which defines an entry point to its feature. In this simple example, we have a counter feature and a decimal feature. Clicking on the Adjust Decimals button opens the decimal screen, so the counter module needs to depend on the decimal navigation module. The navigation module is small. It just contains a routers class, which will contain a router object corresponding to each trio in the feature module. A router object is parameterized with the types that define the trio's public interface, the arguments to instantiate it, the props that it uses for active communication, and, if desired, the result that the trio returns. Arguments are a data class, often including primitive data indicating starting values for a screen. Importantly, the routers class is annotated to declare that it should be added to the router's plugin point. This annotation is part of an internal KSP processor that we use for dependency injection, but it essentially just generates the boilerplate code to set up a Dagger and multi-binding set. The result is that each router's class is added to a set that we can access from the Dagger graph at runtime. On the corresponding trio class in the feature module, we use the trio router annotation to specify which router the trio maps to. Our KSP processor matches these at compile time and generates code that we can use at runtime to find the trio destination for each router. The processor validates at compile time that the arguments and props on the router match the types on the trio. It also validates that each router has a single corresponding destination. This guarantees runtime type safety in our navigation system. From the view model, we can easily use a router to create an instance of a trio, and then push it onto our trio stack. The router ensures that the proper type of arguments is passed and handles instantiation of the trio for us by looking up the destination in the Dagger graph and creating it with the proper initializer. A nice feature of our router system is that it allows us to specify interceptor chains that can provide intermediary screens before showing the final destination. We use this to redirect users to the login page when required, and also to show a loading page if a dynamic feature needs to be downloaded first. If we want to instead start a trio in a new activity, the router also provides a function to create an intent for a new activity that wraps the trio instance. We can then start it from the view model using trio's activity mechanism we discussed earlier. When a trio is started in a new activity, we simply need to extract the parsable trio instance from the intent and show it at the root of the activity's content. We can also start activities for a result by defining a result type on the router. In the view model, we create a launcher property which is used to start the new activity. For example, if on the decimal screen the user adjusts the decimals, we could return the new count to update our state in the counter. The lambda argument to the launcher allows us to handle the result when the decimal screen returns, which we can then use to update the state. This furthers our goal of centralizing all navigation in the view model while guaranteeing type safety. Let's look at another example to demonstrate how trios can be stored in state. This is a simple message inbox screen composed of two trios side by side. There is a list trio on the left showing inbox messages, and a details trio on the right showing the full text of a selected message. The two trios are wrapped by a parent screen. It is responsible for instantiating the two children, passing along data to them, and positioning them in UI. The parent state includes both the message data as well as the child trios. The parent's UI decides how to display the children, which it accesses from state. With Compose UI, it is trivial to apply custom layout logic. Here, we show the screen side by side when the device is in landscape. But in Portrait, we show only a single screen, depending on whether a message has been selected. Both child screens need access to the message data so they know which messages to show. But how do they get that data from their parent? The answer is props, which is an important concept that I've so far glossed over. Props are a collection of Kotlin properties held in a data class and passed to a trio by its parent. Unlike arguments, props can change over time, allowing a parent to provide updated data as needed throughout the lifetime of the trio. Props can include lambda types so that a screen can communicate back to its parent. A child trio can only be shown in the parent that supports its props type. This ensures compile time correctness for navigation and communication between trios. Let's see how props are used to pass message data from the parent trio to the list and details trios. When a parent defines child trios in its state, it must include the type of props that those children require. For example, the list and details screen each have their own unique props. The list screen needs to know the list of all messages and whether one is selected. It also needs to be able to call back to the parent to tell it when a new message has been selected. The detail screen just needs to know which message to display. The parent view model holds the child instances in its state and is responsible for passing the latest prop values to the children. So, how does a parent trio pass props to its child? In its init block, it must use the launch child initializer function. This function uses a lambda to select a trio instance from the state, specifying which trio is being targeted. The second lambda argument receives a state value and returns a new props instance to pass to the child. This function manages the life cycle of the child, initializing it with a flow of props when it is first created, and destroying it if it is ever removed from the parent state. The lambda to rebuild props is invoked again every time the parent state changes, and any new value of props is passed along to the child through its flow. A common pattern we use is to include function references in the props, which point to functions on the parent view model. This allows the child to call back to the parent for event handling. Props can also be used to pass along complex dependencies, which forms a dependency graph scoped to the parent. Before a child trio can reference props data in its UI, it first needs to be copied to state. Child view models override the function update state from props change to specify how to incorporate props values into state. The function is invoked every time the props value changes and the new state value is updated on the view model. This is how children stay up to date with the latest data from their parent. For non-state values in props, such as dependencies or callbacks, the view model can access the latest props value at any time via the props property. For example, we'll do this in the onMessage selected function. The list UI will invoke this function when a message is selected, and the event will be propagated to the parent through props. There were a lot of complexities for us when implementing props. For example, when handling edge cases around the trio lifecycle and restoring state after process death. However, the internals of Trio hide most of the complexity from the end user, and overall the prop system has been a success for us because of the type safety and explicitness it provides. Having an opinionated, codified system for how compose screens communicate has really helped to standardize and improve productivity for our engineers.
Thanks, Eli. Now I'll go over a series of UI patterns that Trio provides to accelerate developer productivity. First, we've added a mechanism to our navigation called UI presentation types. Each Trio's UI class supports at least one presentation type and is enforced at compile time. UI presentation types map to various ways a screen can be presented from a navigation router, such as a full pane or a bottom sheet. This differs from fragments where they are not aware of how they are being presented. Sometimes it is important to draw UI differently depending on the context, such as whether the toolbar needs to be configured and whether the status bar color needs to match the toolbar. To show a trio as a full pane, its UI class has to implement the full pane interface. This interface requires implementation of the full pane content function. This works similarly to the content function we explored earlier, except we now have the guarantee that it is only used when the trio is shown in a full screen context. The trio's corresponding router has to implement an equivalent interface, indicating that it can be shown as a full pane. Sometimes a trio is used in different contexts and needs to support multiple presentation types, such as both full pane and bottom sheet. The UI class then implements additional interfaces for each presentation type. Following the same pattern, the bottom sheet interface requires implementation of the bottom sheet content function. The two content functions can share composables while also allowing customization specific to each UI presentation type. Similarly, we add the bottom sheet router type interface to this router. The router interfaces make clear which presentation types are supported and add explicit functions that callers use to create a trio. A common UI pattern is to use a backstack of screens for navigation. Earlier, we showed how a trio can manage a list of children in its state to accomplish this, but it's tedious to do that manually. To help with this, Trio provides a standard ScreenFlow implementation, which is a reusable parent screen that manages a stack of Trio screens in its state. All screens in the ScreenFlow must share the same navigation props type to standardize the API for pushing and popping screens. Pop allows a trio to pop itself off of the navigation stack. If this is the last screen in the current navigation stack, then the ScreenFlow will be finished and will return to the previous navigation stack. Push allows a trio to push a screen on top of the current navigation stack and initialize it with starting arcs. Push for result allows registering a screen launcher with a callback for when pop with result is called. Navigation props is the standard props interface for providing the ability to push and pop screens in the navigation stack. By default, when a trio is shown in a new activity, it is automatically wrapped in a screen flow so that it has access to these standard navigation calls. In the interest of standardizing screen designs, code patterns, and reducing boilerplate, we provide default screen scaffolds for the Trio UI. These scaffolds standardize common component slots such as the top navbar, main content area, loading indicator, footer, and alerts. Our most common scaffold is full pane lazy list. As the name suggests, this is a scaffold made for full pane presentations and supports lazy list rendering in the main content area. The scaffold function takes various arguments to customize the screen. For example, navbar args can control the navigation icon and title. We can also easily change the status bar color. Another common use case is alert dispatching. We can trigger alerts based on values in our state, such as network error states. Our scaffolds provide other common configurations as well, such as loading states, footers, and scroll behavior. Now, I'll go over our testing approach with Trio. Each trio is required to define a mocks class, which contains mock state values to use for tests and previews. The mocks class types have to match the types declared in the trio class. The mocks class specifies a default state provider, which provides a standard state for the trio. A default props value is specified in order to mock out any dependencies provided through props. Lastly, a presentation type is specified, indicating how the mocks should be presented. This is important if the trio supports multiple presentation types. Altogether, the default mock represents a canonical, fully loaded state of the screen. In addition to the default, variations can be defined to cover other possible states for the trio. For example, we might specify a variation that uses a decimal value for the count. To simplify the task of defining state variations, we use the Mavericks setter DSL, which is provided in the Mavericks open source repo. This DSL allows us to chain multiple state changes and allows setting deeply nested properties. We try to define mocks variations to cover cases such as null values, empty lists, and network failures. Trio provides a robust set of testing frameworks that leverage the mock state. We have a library to make unit testing the view model simple. We define how we want the view model under test to be created. The create trio VM initializer function helps initialize the view model with a mock state and props from its mock class. The test framework provides a DSL to describe what state change we expect given a view model function invocation. Here, we verify the behavior of the increment count function by asserting that it increments a state by 1. Besides for testing state changes, there are also helpers to validate other common scenarios, such as props updates, navigation calls, and network request executions. In addition to unit tests, we found screenshot testing to be immensely valuable at Airbnb. Trio standardizes this by using KSP to generate a screenshot test for every Trio implementation. The generated screenshot test instantiates the Trio UI and renders it using the values from the mocks class, including different presentation types. The test validates that neither the view model nor diagraph is accessed during composition. This helps us enforce best practices for compose and avoid potential misuse. Trio's screenshot testing is built on top of Paparazzi, which we love for its speed and reliability. Our tests programmatically loop through each mock variation and create an initial state using the mock's default props provider. We also leverage the UI presentation type in order to take appropriately sized screenshots. Our approach to screenshot test generation means that engineers write zero traditional screenshot test code for their trios. All they have to do is define their state mocks, and the rest is automatically generated. We employ a somewhat novel testing approach that we call automated interaction testing. Similar to screenshot testing, each mock is used to render the UI, and then our test runner iterates through the UI hierarchy and programmatically clicks on each node. The test verifies that no exceptions are thrown and is even able to record outcomes from the event. One of the main outcomes we record is whether any state changes were made to a view model. We can even track which functions were invoked that led to the state change. The results are stored in a JSON file, key to which UI element caused the event. Here we can see that clicking on the counter button causes the count value in state to be incremented. We capture side effects such as network request executions, navigation calls, and coroutine executions. The JSON files get uploaded with each PR, and we diff them against baseline to detect changes in behavior. This has been very helpful to explicitly document the behavior of each click, detect regressions on PRs, and reduce the amount of manual tests we need to write. These interaction tests are generated via KSB, so each trio gets them for free, saving our engineers a lot of time writing tests. Trio supports custom UI espresso tests for use cases not covered by our other testing systems. We find this helpful to test complex interactions between the UI and view model. To demonstrate, let's write a UI test to verify that clicking the counter button correctly increments state and reflects a change on screen. We start with Jetpack's create Android compose rule function for testing composable UI. Trio provides a helper function, render trio with mock, to instantiate and render a trio with its default mock state. This returns the trio's view model, which we can use to make assertions. First, we'll verify that the UI displays the expected text for a current count of 0. Then we perform a click on the button to trigger an increment count call to the view model. Finally, we'll verify that the view model did in fact get the increment count method invoked, and assert that the UI's text is now updated to show a current count of 1. Lastly, we provide tooling to speed up manual testing. Our dev app allows us to build a subset of feature modules so that we get much faster iteration times versus building the entire app. Opening the dev app shows the subset of trios that the developer has chosen to include in this build. Selecting a trio shows a list of the mock states defined for that trio, and allows us to open the trio in any of those states. This makes it trivial to quickly access and test any screen and state configuration in the app. This is particularly helpful for screens that would otherwise be deep in a flow, or states that would require many steps to reproduce. In the example on the right, we open up mocks that specify different UI presentation types, one which launches as a dialog by default, and another as a full pane variant.
I'll wrap up with a summary of what Trio adoption and experience looks like at Airbnb. We started designing Trio in late 2021, with the first Trio screen seeing production traffic last year in mid-2022. As of this month, we now have over 125 Trio screens with production traffic at Airbnb. From developer surveys, we've heard that many engineers really enjoy the Trio experience. They like having clear and opinionated patterns for scenarios that were difficult with fragments, and are happy to be in a pure compose environment. Overall, they report faster development cycles and cleaner code. To support our engineers, we have invested in IDE tooling with an in-house IntelliJ plugin. It includes a Trio generation tool that creates all of the files and boilerplate for a new Trio, including routing, mocks, and tests. The tool helps the user choose which arguments and props to use, and helps with other customizations such as setting up custom flows. It also allows us to embed educational experiences to help newcomers ramp up with Trio. One piece of feedback we heard from engineers was that it was tedious to change the args or props type of a Trio, since it is used in many different files. We leveraged our IDE plugin to provide a tool to automatically change these values, making this workflow much faster. Our team leans heavily on tooling like this to improve the experience of engineers at Airbnb, which we found to be really effective. We've even adopted Compose multi-platform for development of our plugin UI. This has made working on it really enjoyable and also makes it more feasible to create complex tools like this. Overall, Trio has been a great success for us, and we're happy with the design choices we made. One change we are anticipating, though, is how we will incorporate shared element transitions between screens. We've been waiting for finalized composed APIs for this, and once they're available, we'll likely have to redesign our navigation APIs to accommodate them. We're also planning to publish an article later this year about Trio. It'll go into more detail about things we had to gloss over here due to time. If there is anything in particular that you're interested in learning more about, please let us know. Thanks for listening and letting us share what we've been working on at Airbnb. Our Android platform team works on a bunch of cool stuff like this, and if you'd like to learn about another great project we've been working on, I'd recommend checking out our teammate Ben's talk this afternoon on supercharging Android Studio performance. He's going to cover our efforts to improve IDE and build speeds. So thank you all for attending, and I think we have a few minutes for questions if anybody has any. saw you raise your hand. Yeah.
Do you feel that adopting Trio increases the complexity of onboarding new hires in the company?
Does adopting Trio increase the complexity of onboarding new hires? Kind of. I mean, assuming most people come in with some background of views and fragments, they have to learn Compose, a lot of them, and then they need to learn Trio. But we've heard that, like, we've created a lot of code labs and documentation, and people have liked those. So I think mostly what we heard that it's an easy ramp up. Even with fragments, we had a lot of in-house patterns for how to use fragments, which required a good amount of onboarding. So I don't think Trio is significantly different from that. Yeah.
So it seems like with Trio, you need to have all your screen attributes. But what about backwards compilation? Is there any sort of helper classes or functions that you can use to have these legacy fragments?
Sure. So basically, how do we interop here? So you do not need to migrate everything at once. That would be impossible for any large company like us. We invested a lot in interop. So you can start a Trio in a new activity if you want, but we also added support to wrap it in the fragment. So we showed our router class. We have a nice helper function on it that basically you invoke on your router and it returns a fragment wrapping your Trio. And we also have tools to basically share a view model with other fragments. So if you have existing fragments that have a Mavericks view model and you want to create a Trio that can reuse that, we have an adapter that basically converts that view model's state flow to props for that Trio. So the interop story is pretty good. We don't currently allow, we don't have ways to put Trios in a fragment right now, only because our fragments all rely on a custom activity that does a bunch of stuff for like the toolbar and status bar. And we're not quite compatible with what Trio expects for its activity. But it's been sufficient for our interop purposes and migration. So we're migrating incrementally with that.
Would there be a use case where you want to mark a legacy activity that uses that Mavericks model as a Trio and incorporate that into the state as
I don't quite follow. Can you say it again?
like if I want, because you're adding the Trios within the state, right? So if I want to wrap, let's say, a fragment as a Trio without having to kind of convert it all, would I be able to do that?
Wrap a fragment as it, well, you wouldn't wrap a fragment as a Trio. You would start, if you want to open a fragment from a Trio, you could start it in a new activity. Or you would wrap the Trio in a fragment and then have those two fragments in an activity. Yeah. Yeah.
Do you have a timeline to open source?
We're talking about it internally. A little hard because of all the tools we showed around it. Yeah. So we showed some of the testing tools that we showed. Those all rely on mocking the view model. So we basically have a helper function that you give it a Trio class, and using reflection, it looks up the mocks. It creates a mock version of the view model with whatever state you want from the mocks class, and it renders it to preview. Ooh. So like I mentioned, my teammate Ben is giving a talk all about that this afternoon. It's pretty fast. 25 seconds or something, P50, incremental? Maybe 2 minutes? Yeah. Any other questions? Yeah.
Does this support non-instrumented testing like with RoboElectric?
Yeah, so the UI tests we showed are all they all use RoboElectric, so they run on JVM, no device needed. We do some end-to-end testing on device, but that isn't specific to Trio. We do that just across the whole app. Yeah, so the tests are really fast, and they run in each of their own modules, which is fantastic for scalability. No more questions? Yes.
How do you use, you have an activity inside your view model, like you have a reference activity, so can you use the unit test on the view model?
Can you use the activity in a unit test? Is that what you're asking?
No, the view model.
The view model has an activity reference within it.
Yeah, so if you want to use unit test on that view model, you need a reference, need to import an activity.
Yeah, which is fine because RoboElectric provides that. So in that view model testing example that Yvonne showed, we had a function to initialize or create the initializer with mock values. And so that single line sets up the view model for you with all of the activity flows and props flow and everything mocked out. So the view model works as expected in the unit tests.
So you must use it for UI test, not do instrumental tests.
RoboElectric allows us to provide a mocked activity in unit tests, non-instrumented.
Hi. I noticed your trio view models had reference to activity, or in some cases, multiple activities. How are you preventing memory leaks there?
Yeah, so it's all managed by Trio internals. So we provide the view model gets a flow of activities. It doesn't have direct access to the flow, but it has access to helper functions that basically are suspend functions that give it the next value. Trio's internals ensure that that activity doesn't get held incorrectly. The view model technically could use one of those functions to get the activity and then store it in a property. If somebody really wanted to do something bad, we've never had an issue with that, and also things like leak canary with automated tests help detect that. Yeah. So yeah, basically we built a lot of guardrails and automation or tooling around doing it safely is the answer. And it's worked really well for us.
Cool. Thank you.
Yeah. Yes. It's pretty much decoupled from Compose, so yeah, we don't need to plan our updates around Compose updates. So you're asking about animations from Compose during navigation? We do use Compose APIs for that, just standard Compose animations. We will need to update Trio navigation APIs when shared element transitions are more supported. That's pretty much it. Yeah. Okay, I think we're at time. Are we at time? Maybe. All right, no more questions? All right, thank you so much. Appreciate you coming.